Today is the last session on linear models. We'll reach an end. Next week we start to move on to the nonlinear, more complicated stuff, right? And this is going to be the ultimate linear models. After what we have today, you should forget about what we have learned so far. They're no longer important. So. Yeah, that's the main point. So this is the ultimate tool for linear models, and it includes the standard linear regression stuff as a special case. So it's going to be a dominating model. So it has better solutions and more justified. Everything is better. So in the future, if you believe you're doing linear models, this should be the starting point. There's no need to go back to what we have earlier. And what we have done was mainly for the purpose of communicating with old school people, right? That's done. So the last time we talked about subset selection. We said in linear models, the main challenge is about selecting the variables. So we have a bunch of x. We need to decide whether to include each of the x, right? So there were a lot of both conceptual and computational issues. Where's my? Let me open that. So last time we were here, we say in traditional view of linear models, we need to do model selection. We try to split the task into two steps. The first is within the groups. So we group the models in terms of their number of predictors. All those with two predictors belongs to this group. There are so many so many models in the group. They all have two predictors, so we can choose them within the using the R-square or this kind of in-sample performance measures. And for each group, eventually we should have a champion in that group. Then the next step is to compare the champions across groups. So we have the best model with one predictor, the best model with two predictors, and so on and so forth, right? And we talk about how we can choose the champions, and we can use cross-validation. So this is the subset selection, right? And the issue there is really we are facing a binary choice. For each predictor, for each x, we are basically saying, do we keep that x, so that's a 1, or do we ignore that x, a 0? For every x, we're making a 0, 1 choices. And because there are so many x, so we have a combinatorial, a big number of decisions, right? But the real concern is we are saying 0 or 1. Keep it or have everything there. And what we are going to do today is to introduce something in the middle. I don't want to completely ignore that x, but I don't want to have that x 100% in my model. I want to have 50% of that x, right? How do we do that? And once we introduce that thing, we can basically keep an x partially in our model. And that leads to a much nicer, much flexible kind of a model. So we have a lot of other kind of flexibilities in selecting what to keep in our model, right? So that's the main point. At the end, you will see we will no longer have those kind of 0-1 decisions, and every predictor, every x can be part of my model, but my decision is how much I want to keep that, right? So before we move on to the math stuff, so we are going to introduce this several different tools, but they all belong to the family called the regularized linear models. So we're still talking about the linear models, but the main idea is to shrink the model and to regularize. So instead of having 100% of these variables, we want to have some percentage of those variables, right? So before we get into the math, I'll show you some highly stylized a baby problem, right? But this is a baby problem we teach in a PhD class. So don't worry too much about the details. I will try to describe the details. So I have uploaded this file on IVLE. Right? So the story is about, this is a simulation study. Right? I have a true population that looks like this. So this is the true f function in the population. And I only have one x, one y, the simplest possible kind of setup. But just the issue is this f is a sine curve, right? It's not linear. X is in the range of -1 to +1, and y is in the range of -1 to +1. Right? That's my population. So my whole task is I'm getting data from this population, and I want to uncover this structure as many as I can. Right? So this is a trivial problem in the sense that we don't have noise at all. So this is a curve, and once you ask for data from this curve, I'm just going to pick some points on this line. Right? I'll give you some points on this line. So when you can obtain as many points as you want from this curve, this is a trivial problem. There's no noise. You can just connect the points and you get a sine curve. The challenge in this problem is you will only have 2 points. Okay? You will only get 2 points on this curve, 2 random points. Okay? Okay? So this is a simulation. This is the truth, the answer. So I'm showing you the answer first. Then let's see if we have a data sample with only 2 points randomly everywhere on this curve. What can we do to uncover some truths? Of course, we won't get the curvature because we only get 2 points, right? But let's see what can we do at most. Right? So if you have 2 points, what do you do? It's a linear regression. Right? If you run a linear regression with 2 points, you will get a line connecting these 2 points. Okay? So that's one solution. Do we have other better ways? Other better ways? There's a better way. It's counterintuitive. The alternative, let's think about the alternative. Alternative is I'm just taking the average of the 2 y's. Right? So I have 2 points, x1, y1, x2, y2. Right? Connecting that 2 points gives me a line. Alternatively, I can ignore the x. So that's the norm model we talk about in linear regression. The model without any x. I'm ignoring the x. I have y1 and y2. I take an average. I use that average to predict. Right? The norm model. Right? So that's at least that's the 2 things we can do. Right? This sounds ridiculous, right? We have x. We don't use that. But let me show you the 2 models. So this is a quick example. You have 2 points. 1 point on the upper right corner, the other point on the lower left corner. Right? So the blue line is a result of a linear regression. It's going through the 2 points and fit a line. Right? There are only 2 points, so there's nothing you worry about. And the black line is the norm model. So I take the 2 y's and take an average. I'm predicting every future point with that number, the average of y1 and y2. Okay? So there's a red line. We'll come back to that red line later. But among the black and blue, which one do you think performs better out of sample? Why? Yes, but think about the truth. Even it's a finding curve, it has a. Ooh, does it work? Where am I? So think about the truth is something like that. Right? Even if suppose you have infinite number of points, you have all these points. And when you're running if you have infinite number of points, is it better to do a line or is it better to do a constant? Right? If you do a line, you would roughly get something like this. Right? If you do a constant, you get a 0. Right? They all cancel out. It's symmetric. Right? The line would perform better. Right? If you have an infinite number of points. But now we have 2 points. What's the difference here? Okay, let me show you. Right? So is that clear? We only have 2 points. So, but give me 2 points, I know how to do these 2 lines. Right? The blue line and the black line. I know how to do that. So now the point is, I'm not sure how well my line will perform. So I want to repeat this many times because my data sample is random. So I want to draw 2 points from the population, from the sine curve, and do this. Repeat this whole process 1,000 times. Let's plot all these 1,000 lines, and let's see what's happening. So this is the first model, the constant model. Right? Every time I get 2 points, I take in the average, I get a horizontal line. Right? The 2 points are moving around on this true S-shaped curve, but average is somewhere in that range. Right? I'm getting that. And it's not surprising the majority, this is an overlay of 1,000 lines. Right? But the majority is around 0. Right? It's symmetric. On average, it should be 0. Right? Nothing special. But every time, there's 1,000 runs, you get quite different lines. Sometimes it's higher, sometimes it's lower. Right? Depending on your luck, you get 2 points. It can be anywhere. Right? So that's not the worst. Let's see the linear solution. This is a linear solution. Right? Give me 2 arbitrary lines, points on this blue line, connected. You can get all of these crazy things. Right? So what's the problem? If we compare these 2 models, model 0 and model 1, what's the problem? Can you see, let's say first, on average, which one performs better? On average, this guy is about 0. Right? It's roughly symmetric. So on average, you know you are having a horizontal line at the level 0. How about this? Can you visualize on average what's that? Is that a flat line? Is that going upward or going downward? Going upward, right? So roughly, on average, it captures the upward pattern of the population. Right? So you will never be able to capture the curvature with 2 points, but you at least get the upward pattern there. So on average, this should be better. Right? But what's the problem here? It's the variance. Right? So we talk about the bias variance. Yeah? So this is how to numerically measure bias and variance. So so we can actually, how stupid this is. So we can actually measure for these 1,000 lines, we can average this 1,000 lines. So we get, for the first model, we get the red line here. So we just take an average. Okay? And we can also measure the variability. Right? We have this 1,000 lines. For each x, there are 1,000 points. Right? For each given x, vertically, there are 1,000 points because there are 1,000 lines going through that point. I'm measuring the standard deviation of these 1,000 points. Right? For each x, I can do that. So I can do that for all the x, so I can measure the standard deviation everywhere. But here, all the standard deviation are the same, regardless of your x, because they're all horizontal lines. Right? So that's the standard deviation. So in the end, you can. This is how we do the bias variance decomposition. So the model, the norm model, at least average to the red lines. So the red lines are not perfectly fitting the true blue lines, and the difference is the bias, right? Because you are assuming a constant horizontal line. The best possible constant horizontal line is the red guy. It can never capture the blue ones. So the difference between these 2 lines are the bias. And the out-of-sample performance error is not only the bias, but also the variance. And the gray area indicates the variance of that model, right? How variable it is. So let's see the other guy. This is the other guy, right? So we say that the linear model, on average, is perfect. This is pretty much the best line you can have, right? Averaging over this 1,000 lines. The red one is pretty much the best possible straight line you can come up with, minimize. But there's still some bias. There's still some bias because it cannot curve like that. But what's killing this thing is really the variability. We have seen this 1,000 lines can go anywhere, right? So we can measure the variability just like before. We can plot so this up range is the average plus 1 standard deviation, right? Somewhere it's more variable, somewhere it's less variable, depending on your x. But that's the variability, right? Okay, so that's a message of these two pictures. And which one performs better in terms of predicting out of sample? In terms of out of sample mean squared error. Right? So we said the error is a sum of bias and variance, right? And this guy has huge variance here. So this basically dominates everything. I can show you the numbers. Where's the numbers? You see the numbers? So just focus on the first two lines, right? So I'm calculating for these two models, I'm calculating their bias and their variance, irreducible error and out of sample mean squared error. There's no irreducible error in this problem. There's no uncertainty, right? So it's zero, basically. But in terms of bias, the linear regression problem model is much better, right? It captures the upward trend. Constant doesn't work well. But what about the variance? Constant has much smaller variance, right? Linear regression can go crazy. So in total, the mean squared error is the sum of that two terms. So in that sense, the constant is better, right? So that's a key picture. Right? So what's the message here? It's very hard to believe that having a population like that, you would rather go for a constant prediction than linear prediction, right? But the issue is you only have 2 points. Having 2 points is not enough for you to fix the line. Right? The 2 points can be anywhere, so that's not going to give you enough information to fix that line. When you have 5 points, definitely you can try. 5 points would be enough to fix that line. But just having 2 is not enough. Your line can go anywhere. You're subject to a lot of noise, in a lot of randomness in terms of where the 2 points show up on this curve. Right? So that's a issue. And that's a nice illustration of the bias and variance trade-off. One model has a better bias but worse variance. The other one is the opposite. Okay? Okay. So the next question is, how do we fix that? We just said this is exactly the problem we are facing in subset selection. This is a problem. We have only one x in this data set. We are basically struggling. Do we take that x in our model? That will be h1. Or do we not take that x in our model? That would be the model 0, constant. Okay? We only have one, so we can only decide for that x 0 or 1 decision corresponding to the two models. Right? And this is the binary decision. If we don't keep that, we have a constant. If we keep that, we run linear regression, we get that line. So that's binary. Right? So the idea for today is really, I don't believe in this straight line linear regression thing, but also purely using constant is not smart enough. I'm having 2 points, and at least I want to capture some upward trend out there. Right? How do we do that? And can we take 50% of that x in my model? I don't want to take 100% of that. That's going to overfit in some sense, right? So that's the idea. So, and if we have that, let's think about how do we take this x partially. Okay? This x carries some information about the underlying this fx, right? But just take that directly is not going to help us. Just too random. So how do we solve this problem? And the idea is, let's look at the idea. Where's my line? The idea is the red line. If I'm doing 0 or 1, I'm struggling between the black one and the blue one. After all this analysis, I realized in my problem, the black one is better than the blue one, right? Constant is better, even better. But I still hope there's some information I can dig out from this x. I still want to include that x, but I don't want this line to go anywhere, right? I don't want the lines to go crazy, like almost vertical. Right? That's my problem. So the idea here is, can we just rotate this line slightly downward? Right? You can see there's a pivot point. Right? So to come up with a new line, so we need the two parameters, the intercept and the slope. Let's first agree on the slope. Slope being the original is too much. Slope being 0 is too little. Let's keep some partial of that slope. Right? That's what we are doing here. But how much to take is a decision. Later we will optimize that. For now, let's just say we take 50% of the slope. Right? We take the original blue line. We find the slope. We take 50% of that. Then it's about the intercept. If we fix the slope, we still need to move that line up and down to find the intercept. Right? So in here, we have a magic point. Can anybody spot what? What's that point? What's going on here? 0, 0? Oh, no. What's this point? We talk about this in regression. Right? Yeah. So this is x bar. This is y bar. Right? We said when you do regression, when you fit the line should always go through x bar and y bar to minimize the error. So that's a pivot point. You should never deviate from that point. And if that point is fixed, the slope is given, then we're done. Right? We solved the problem. So we can take the original blue line, fix that point, cut the slope by half, and we have the red line. Okay? But the real problem is much more difficult than this one. Here we only have one x. Think about it. You have x1, x2, and x25. You need to reduce their slope. How do you do that? Later we'll talk about the general version. But this is for illustration. Right? So if we can agree on that, let's see. Let's just try. And this is just an intuition. Intuition says x must have some information in there. We shouldn't just ignore that. But we cannot take too much of that. So let's just press the slope down. So again, we repeat the whole thing. We call this H2. This is model 2. Can you make a comparison of these two pictures? Do you see an obvious difference? So it's flatter, right? This 1,000 lines in model 2 is flatter by definition. Basically, every line corresponds to another line in the picture up there. It's half of the slope. So everything is flatter, centered towards the middle, right? And what's the benefit of that? So we can repeat the same thing, measure the mean of these 1,000 lines. We have the bias and variance. So we can compare these two. You see the benefit? The benefit is clear. The variability is much smaller, right? Because we squeeze every line down towards the flat line, right? So it cannot fluctuate too much, right? So it's on average, there's a less variability pretty much throughout everywhere. Right? What about the bias? What about the red line? Huh? So the red line is getting better or worse? Worse, right? So we just said this is pretty much the best possible straight line to fit this S-shaped curve. And by squeezing that with half of the slope, we are increasing the bias. So the whole idea of regularization for today is we can sacrifice the bias a little bit, but what we gain is on the variance side. The variability can be reduced by a lot. So we lose on one hand, so we gain on the other hand. But the gain is hopefully the gain is larger than the loss. Then we improve the out-of-sample performance, right? But this is just a hope. It may not. You're losing on one hand, right? So it's just a hope. So we can measure that. So we put the third model in there. You can see the bias is in the middle of the previous two, but it is worse than the linear model. But the variance is going down by a lot, right? Okay. Overall, the sum of the two, the mean squared error out of sample, is way better than the linear regression solution. But it doesn't solve our problem. Our best model was that one, right? It doesn't beat the constant model, right? Beat the linear model is not our point, right? We know that's not a good thing. But at least we get a direction, right? We know the linear model is bad, but at least we get a direction by reducing the slope, we can improve, right? And for now, we are just trying 50%. Nobody said 50% is the best you can do, right? We can try to optimize that. So next, let's try to find the best amount of shrinkage. So we want to numerically optimize that. So we just try, for any given alpha, we can do this whole process, right? We just try alpha going all the way from 0 to 100%, right? By the way, if alpha is 0, what's the model? If alpha is 0, it's the constant, right? So we take whatever slope, multiply that slope by 0, we get a constant line, right? So constant model is basically a special case of what we're talking about. If alpha is 1, it's a linear model, right? So the model we're talking about is the two models we just talked about were just special cases of what we have here. So by sliding between 0 and 1, we should be able to find a good alpha somewhere, right? That's a hope. It may not, the optimal alpha may be just 0. That's possible, but we have the hope. So we just repeat the whole process. Don't worry about the code. And we end up having this picture. What do we see here? I'm using this again. Don't jump. So this is alpha on the horizontal axis. Alpha is 0 is our model 0, right? Our model 0, we have a mean squared error. We have this is MSE. Which one is bias? Mean 0 has a higher bias, so this is bias. This is variance. Right? That's model 0 we have just tried. And this guy is model 1 we have just tried. Linear model with a huge MSE because of a huge variance. It has smaller bias. Right? And we have been sliding in the middle. We tried 0.5. We said 0.5 is not good enough. But we can try other ones. Right? So at the end, the ultimate choice depends on the mean squared error. Right? We want to choose the model that gives us the smallest out-of-sample error. And that seems like a hopeful. Somewhere here, you get a better one. Right? So it's here already. So the optimal alpha I found is 11%. And with that alpha, my mean squared error is 0.752. Not very readable. 0.752. What was the original? 753. So we made some progress. Right? But the point here is, first of all, we find an improvement. Even if we didn't find an improvement, we don't lose anything. We can always go back to model 0 at the very beginning. Model 0 is a special case. So we will never lose anything by doing this whole process, right? And then the next thing is we realize, hey, there's some alpha in the middle can improve the overall performance. And that alpha is not a 0 and 1. It's somewhere in the middle. So we're essentially including this x partially, right? Including this x partially. And that actually is going to give you a better solution, right? So that's the overall idea. That covers the overall idea of regularization. The model selection is no longer a 0-1 decision. We can, at the same time, play with the coefficient, play with the slope. We can make the slope slightly smaller and to control the overfitting, all these things, right? All good? So this is just a, yeah?
Because of the only 2 samples, right?
What do you mean by the
sample, we still have this problem, this randomness.
What problem?
Randomness.
Where is that?
Randomness is what I mean.
Oh, okay, I see. So why these lines go everywhere?
No, I mean, because in real case, we have a lot of data, lot of samples instead of just 2. We have this issue.
Yeah, you have noise, right? Here, I'm trying to make this problem trivial. There's no other things. You have noise, right? You have noise, your lines go everywhere. You always have a model selection issue, right? You always need to decide, do I include this x or not? Is that a better thing to do it or not? It's always a 0-1 decision. The point I'm trying to make is you can do that by 11%. And you can try. You will never know whether they will improve your problem, but that's something we can try, right? That's not dependent on this whole thing. This is an exaggerated version of the problem when you have 2 points, but that's clearly deliver the point, right? Without this regularization, you would go for the constant, right? You're using the previous thing. Mm-hmm. Yeah. Yeah. Mm-hmm. Mm-hmm. You always face the, yeah. No, you always face a model selection issue. Just like the exam, you have 20 columns of noises, right? You never know their noises, right? Somebody give you this data. This is the data. Go ahead and fit the model. And you fit the model, you get several variables in there, right? That's you cannot differentiate, right? No. MSE use out sample. I have a test data set. This is a simulation, so I have a huge test data set to measure the out sample performance. In sample, there's no error. Just 2 points. Get a perfect fit. No error. All right. So that's an exaggerated version of regularization. This is simple because when you have 2 points, you know exactly how to find that line. So I can skip the algorithm. So that's the point of this small example. When you have 3 points, you have to talk about the algorithm, how to find that line. That's a bit too much, right? But now we can move on and talk about a general situation. So the finding here is somehow we can still solve a linear model. And we can improve the performance of the linear model by reducing the slopes, right? By reducing the slopes, you're essentially making your y prediction less dependent on the x, right? Before it was like this, but you're reducing the slope, it's less dependent, so it's less variable, and you're controlling the variability, right? So coming from there, we can try to, do we have a general way of find the coefficients, the slopes, and how do we reduce that, right? So the first solution is the so-called ridge regression. So it's built on top of a linear regression. So we said linear regression is the blue line we just seen. It choose the line to minimize the in-sample error to fit your data points as much as possible. So that's not what we want, right? But this is how we got the blue line in general if you have n data points there, right? And we just realized that's not the best thing. And when we find our lines, we want our lines to be less steep, right? So we want to control the slopes. So the idea of ridge regression basically says, if you want to do that, you can just replace the objective you had before in your linear regression and add an extra term on that, right? So that's the original residual sum of square in your original linear regression. So I'm saying that's not everything I want. That's partially what I want. At the same time, I want to minimize the slopes in some sense. Here, the some sense means the square. I want to minimize the squared value of the total slopes. I have a p predictors, and for each predictor, I have a slope with respect to that x. So I want to minimize the sum of these slopes. I want to make them less steeper. Okay? How many of you were taking the optimization class? Okay. So a lot of the things today is just related to the optimization class, and yeah, you're doing this in a wrong sequence, and yeah. Let me try to explain. Okay? So this is a standard way of doing things in optimization. I basically have two objectives. I want to find a line to fit my points. That's the original objective. At the same time, I want the betas to be small, because just now we have that example. If the beta is small, we are potentially benefiting from there. There are two objectives, and how do we kind of strike a balance between the two objectives? So the standard trick is let's add a lambda here. So lambda is basically the weight, or basically the measures the trade-off, right? Lambda may take different value. The larger the lambda, the more emphasis you put on one side, less on the other side, right? Think about what if lambda is 0? What do you see? Right? If lambda is 0, we go back to the original solution. Right? If lambda is infinity, what do we do? What do you do if lambda is infinity? Huh? Beta is 0, right? If lambda is infinity, think about this as a cost. If you want to increase the slope, you need to pay a lambda dollars, right? And if that's infinitely expensive, you just put all the beta to be 0. And if all the beta is 0, then all the predictors are excluded from your model. You only have one constant. By the way, I forgot to mention. So this beta starts from 1, right? So we have beta 0, beta 1, all the way to beta p. Beta 0 is the constant. We don't worry about the constant. Right? We don't worry about the intercept. What we worry about are the slopes. So we only want to minimize the slopes, not the constant. Right? To extreme, when lambda is infinity, all the beta j becomes 0. You only have a constant in your model. Right? That's the constant model. So, and the question is, how do we decide lambda? Right? Just like earlier, how do we decide the alpha? They're not exactly the same thing, but they function the same role. Right? By changing your alpha, you're placing different emphasis on different things. So let's leave that question to a later point. Now let's think about if somebody can tell me a magic lambda, I can solve that problem easily. It's an easy problem. Just like in linear regression, we can easily solve the minimization problem of the first part. We can equally easily solve that similar problem, just because of the squares. Right? So people introduce all these squares for the sake of easy optimization. So, so that's the whole idea about ridge regression. And lambda is a parameter later we need to decide by cross-validation. Nobody can tell us, so we have to do cross-validation. But given a lambda, this is a simple model. At the end of the day, I can find the betas that minimize this overall two objectives. And I have a linear model. I have a line. Right? Just think about the red line. Give me an alpha, I can find the red line in there. Okay? It is so hot here. Do you feel hot? Leave the door open. You need this one? Good. All right. This is the so-called ridge regression. The only change is in the objective. We add another term, so we are balancing the two concerns. Think about the two concerns, right? On the one hand, we are using the beta to minimize the residual sum of square to find a better fit in sample. On the other hand, we try to control the size of the beta. So that's the name shrinkage. We're shrinking the slopes towards 0 by this term. Right? And the size of the lambda really controls how much weight you put on those two objectives. And we talk about that. There's two extremes. Lambda is 0, and lambda is infinity. We got the two extremes, the blue line and the black line we have just seen. And we use cross-validation to find the optimal lambda. Right? Just like in the example, we actually use simulation to plot that line. So we have a lot of test data. We can plot that mean squared error out of sample. But here, in practice, you don't have test data, so you have to use cross-validation to do that. So later we'll do that. Yes? Sure. Think about this is the price, right? This is the price you pay for increasing your beta. If the price is infinity, and your objective is to minimize your spending by choosing your beta. If the price is infinity, there's nothing you can do. You have to put a 0 here so you don't pay any price. Okay? Think about lambda is a price, or the cost of increasing the slopes. Right? That's by construction, right? The whole idea of including this is I want you pay to have the slopes. And the original problem is you don't pay for the slopes. You do whatever. So you get the blue line. By construction, I want you now to pay for that. So you would control yourself a little bit. So you go down a little bit. Right? So that's just a beta. Lambda is not in. Your final model is still a line. The red line is still a line. You have an intercept and a slope. It's still a line. Lambda is not in part of your model. Once you find your beta, you are done. Okay? It's still a linear model. Yeah?
How this lambda is related to the alpha showing in your...
They're similar, but not exactly the same. But they're similar things. Alpha is not exactly the cost of having the slopes. Alpha is the outcome. So I just say, I just want to cut the slope by half. That's just easier in that example. I give you a cost you don't know how to do. That's the issue, right? We have to solve the optimization. Right? Okay? So another question? That's the earlier. The whole story is I want to make my slopes smaller. Right? I want to constrain myself. Don't fit a line like almost vertical in the earlier example. I want to tighten myself so that I don't go crazy when the data is random. Right? So this is a regularization. The literally means I want to control myself and don't have too much flexibility so that I won't overfit. Right? Yeah, there's only one lambda. Later you will see you don't need to do that because finding lambda itself is a challenging task. You don't need to do that because later we need to. This relates to an important question. There are different x, like in a credit card story. One x is the income, that's in terms of thousands of dollars. Another x is the years of education, in terms of years. So now you say there's one beta for this income, one beta for this education. How do you decide which beta to reduce? Because you only have that budget to have some slopes. How do you decide? It's very hard to compare these two betas. And later we'll do normalization. We need to normalize everything so that all the betas are on the same scale. So you just need one lambda. Yeah. Okay? Mm-hmm. All right. So let me give you a visual illustration of what's going on. That's my favorite part of this. Let's think about a two-dimensional problem. So P is equal to 2. I have x1 and x2. Therefore, I have a beta 1 and a beta 2. Right? Beta 0 is the intercept. I don't worry about that. And let's think about the linear regression. In linear regression, we're minimizing residual sum of square as a function of beta. So you give me beta 1, beta 2. I can plug in that beta into my formula. I can measure the error. Right? Give me a line, I can measure the error. And the error is a square term of that thing. So it's a quadratic shape. Can you visualize a quadratic curve in a two-dimensional space? There's a beta 1, beta 2. And let me just plot it first. Huh? So the error, the ISS, this whole thing is the surface of the error. Right? The error depends on what are your betas. Give me a pair of this beta. There's a corresponding error. But the error is a square term of those betas. So if you plot it, it's like a ball, right? And if you slice that, plot the contour that looks like this. So think about this as a ball coming out of this screen. Right? It's a ball facing you, right? And the linear regression optimization says, this is a ball. I know there's a minimum point. I'm going to go directly to that minimum point. So I basically throw a ball into that ball. That ball will just slide down to the bottom. Right? Where's the bottom? So that's the beta by linear regression. You throw a ball into this ball. You just scroll down to the bottom. Okay? Visualization. Right? Now the issue is we realize this is not the best way to do things. And the better way, potentially better way, is to constrain us, not to go that crazy. What do we mean by constraining? We said we want to penalize on the betas, right? So in our context, in this context, we want to penalize beta 1 square plus beta 2 square, right? There are only two betas in this problem. So where do we see beta 1 square plus beta 2 square on this picture? Huh? Huh? No, I mean, just for that linear regression solution, for that point consists of beta 1, beta 2. Right? That's a point with an x coordinate and y coordinate. Right? I'm asking you, given that point, what's the meaning of beta 1 squared plus beta 2 squared? Circle? If you have to draw something on this picture to indicate that number, diagonal line, this not diagonal, right? You're connecting that to the origin. Let me use a different color. The origin is 0, right? Why is that? This is beta 1. This is beta 2. Right? Beta 1 squared plus beta 2 squared is, this is a square root of beta 1 squared plus beta 2 squared. Right? Okay? So, and in ridge regression, we say we don't like the linear regression solution. On top of that, we have two concerns. On the one hand, we want to go as deep as possible, go to the bottom of that bowl. On the other hand, we want to impose a penalty, impose some money for going far away from the origin. Right? So I want to penalize you on this guy. The farther you go away from the origin, the more money you need to pay to me. Right? Do you see that? That's the distance. Right? For any point you choose, that's the distance you need to pay money, the distance to the origin. Right? So now I'm imposing a lambda on the distance you're traveling away from the origin. Right? So you can think about this lambda as a rubber band. You tie that ball onto that rubber band. The rubber band can be infinitely loose. It doesn't have any force. Then your ball will still go to that bottom, right? So that's when lambda is 0, it's infinitely loose and doesn't have any force. Now you started to tighten that rubber band. And rubber band is pulling that point, pulling your ball towards the origin, right? So your ball will be somewhere on the slope, stuck there, right? And that strikes the right balance between I want to go as deep as possible, but the rubber band is pulling me towards the origin, right? So you get a force, you get a lambda imposing a force to pulling you towards the origin, right? So the resultant solution can be, let me use a different color. The resultant solution can be something like this. This is when lambda goes to 0. This is when lambda goes to infinity, right? When your lambda is infinitely powerful, you just drive the ball back to the origin, right? And there's an optimal lambda somewhere in the middle. Just like earlier, we have an optimal alpha. It says, I just want to take 11% of the slope. It's just like the same thing. Hopefully, along the way, there's an optimal point that gives you a good combination of the two concerns. It doesn't go to the bottom of both, but it doesn't go to the extreme, the other extreme, right? So lambda is controlling where you stay on that blue trajectory, right? On the two extreme, you have the two original solutions. Okay? So your ball will stuck somewhere on the slope, and that's the solution. So that point is going to be your ridge solution. Right? There's a beta 1, there's a beta 2. Right? That's the point. And later we need to choose this lambda. So along the trajectory, there are all possible models. For any given lambda, there's corresponding beta, a pair of beta, so that's one model. So we need to choose the lambda that gives us the best cross-validation error. So that's the best lambda. Okay? Yeah? Uh-huh. Yes. That's not may not be the straight line thing. It depends on the shape of the ball. The ball is a ellipsoidal, yeah, can be like this or this. You'll be at 0 for sure, right?
That means that your solution then tends to some mean.
Yes, yeah, that's no model. Just take the constant average. Yeah. Okay. So that's a visual interpretation of ridge regression. We are trying to deviate from the linear regression solution, and the direction we are trying to deviate is towards the origin, because if we're moving towards the origin, we're having smaller slopes and less variability. Okay. So then this is so we're done with the theoretical part. That's the only extra term. Right? So in practice, what do we do? In practice, we need to decide the optimal lambda. Right? This is not a trivial task. So the software will try many possible values of lambda. And that's basically along this blue trajectory, we need to decide what's the optimal place to stop, right? So software will do this. So we will start from the very left end. So this is lambda goes to 0. Lambda close to 0. You will get your linear regression solution. So every vertical slice of this plot is one model. So the vertical slice is one model. You have your beta. This is one of the beta. Let's say beta 2. This is beta 5, beta 3, beta 1. We have many x out there. And a vertical slice is all the betas. That is, when you impose a particular value of lambda, you solve that optimization problem, you end up having this bunch of slopes. Okay? And the very left end would be the linear regression solution when you don't have any penalty on, don't have any cost on that. And the very right end is when lambda goes to infinity. When lambda goes to infinity, all the betas goes to 0, so they all shrink to 0, right? So this is the null model with no predictors in there. And somewhere in the middle, so any point in the middle is one particular model. This is for any arbitrary lambda. There's a corresponding model with a beta 2 now move down, beta 5 now move up, beta 3, beta 1. Right? So by changing the amount of the regularization, by changing lambda, you are getting a different set of betas, and they all gradually goes to 0. Right? But along the way, it's not necessarily monotonic. You can see here, beta 2 goes down, but somehow beta 5 goes up. Probably these two variables captures very similar information. What is beta 2? Limit, this is a credit limit. This is credit rating. So these two are highly correlated in some sense. So this regression actually picks up these two, gives you similar information. If you need to save your budget for the betas, you save one, just keep the other one. Yeah? You don't lose anything. So that's the idea. But towards the end, you will have nothing if the cost is too high. And hopefully somewhere in the middle, you should know that there's optimal lambda somewhere. Now, later we'll talk about how do we find the optimal lambda. But if you have the optimal lambda, you know this slice is your optimal model. That's a model with linear formulas with all the x and all the corresponding coefficients out there. Right? So that's the gradual changes in your models. And in R, this thing is done automatically, so it doesn't automatically find the range of lambda, cut this range into 100 steps, for each step, it fits the model and plot this line for you. Right? So it helps you to visualize how things are changing over time. Okay. Forgot about that. So this is there's a bug in the original software. So this is not a standardized coefficient. This is the true coefficient, the true betas. Later we'll talk about the standardization. So the bug is fixed, I think, last year. Later when we do coding, you will see you no longer see the standardized thing. These are the actual betas. And the picture on the right-hand side carries exactly the same information, but you just change the horizontal axis. Here, the picture on the left plots everything in terms of lambda. When your lambda changes, how the coefficients are changing. Some people don't like that because lambda is not very meaningful. You say lambda is 10,000 or 100. What do you mean? It's not very clear, right? So you can see lambda goes from 0.01 to 10,000. Right? It's not clear what's the meaning of that. So people instead, some people prefer the alternative way by framing lambda in terms of the distance. So you can see it is a ratio of two things. Do you know this notation? Okay. So this is the distance. This is a mathematical, the most commonly used mathematical distance, the Euclidean distance. Later we'll play with 3 other distances, but this is the most common thing, right? The distance to the origin. So you can see the ratio is the ratio of two distances. The numerator is the distance to the origin of the model chosen by the ridge regression. The denominator is the distance to the origin of the model chosen by linear regression. Right? So it's more straightforward to look at here. So for linear regression, you have beta. So the distance to the origin is the green one. Right? So they use that as the denominator because this is pretty much the maximum distance you would travel. You would never travel beyond that because you don't gain anything. Right? So that's the denominator. And the numerator is this distance. Right? So the ridge regression choose for any given lambda, ridge regression will choose a particular point. What's that distance to the origin? So they use the blue one divided by the green one to indicate how far are you in this range. Right? All the way to this point, this is 100%. All the way to this point is 0%. So that gives you a percentage kind of a measure. So you can see, so this is 0% to 100%. Right? So 0% is lambda goes to infinity. This is lambda goes to 0. So the two pictures are just the same thing, just rescaled on a different plot. Okay. All right. So that's the first step. Give me a bunch of lambdas. I can find these betas. I can connect these betas, plot a nice picture for you. Right? And we mentioned this scaling issue a little bit. So naturally, when you do this thing, you need to make sure your x are roughly on the same scale. So we by definition, we'll do the standardization. So every x would be divided by its own standard deviation. And if you want, you can also shift the means, and that's okay. So to make sure all the x are on the same scale, so all the betas are of the same scale, then you don't need to struggle about different units or different magnitude of all these betas. So this is the standard thing, and in practice we don't do that manually. Software will do that because this is a necessary step So the software will just do that automatically for you. And the output is translated back. So you don't need to worry about the internal. So this is all internal, transparent to the users. Just to highlight, this is a necessary step. Yeah? So don't worry about the normalization part. So back to the beginning, why it works. Right? We just said linear regression is okay in terms of bias. It finds the best fit of the data, so it has a good bias. But it has a really bad variance. Right? By shrinking, we are controlling the variance. Right? That's the whole idea. Yeah? But at the same time, there are two nice kind of a byproduct of this ridge regression. Right? So we just said the whole motivation is to control the slope. But there are two nice byproducts. One is the multicollinearity. I'm not sure whether I covered that last time. So multicollinearity says if the true model in your population is y equal to x, but you happen to have two data, so that's the reality. No, that's the choose, right? That's the choose part. But when you are trying to learn y, you actually happen to have x and x prime in your data set, and x prime is the twin brother of x. They are exactly the same. Okay? It may sound trivial, but it happens a lot. You have two columns that carries exactly the same information. Right? So if you're using x and x prime to fit your data, to try to find the relationship between x and y, you would have many possible models because x and x prime are exactly the same. Right? You might have 2x minus x prime. You have half x plus half x prime. They're all the same thing, right? You have a minus x plus 2x prime, right? Da, da, da. There are infinite number of combinations because your linear regression cannot really differentiate. At the end of the day, you get the same in-sample error in that sense, right? So linear regression cannot handle this situation. This is one of the problems. This is also the problem in your test. Right? The rata 1 and the rata 2, they are highly related. Right? So your linear regression cannot really tell how to allocate weights to this rata 1 and rata 2. And the resulted solution you've seen is one is negative, one is positive. But actually, that's exactly the story here. Right? So in linear regression cannot identify these issues. But ridge regression can easily handle that. Right? Can you see why? If you're running ridge regression, which one is the better model? Right? In terms of the residual sum of square, they're all the same, right? Because the data is like that. But in terms of the other terms, the beta square term, right? You would prefer this one, right? Because you have to pay money to get some slope. You don't really get some crazy 2 and minus 1 there. Both you need to pay money, right? You would do 50-50. That's the cheapest way of doing things, right? So by imposing some cost to that, you solve the multicollinearity issues. Right? Well, that's a minor thing. I don't think that's so important. The real benefit, what makes ridge regression popular, is the second one. The second one says when we solve linear regression, the intrinsic assumption is the number of rows is larger than the number of columns. That's the assumption. If it's not the case, you have multiple solutions having the same thing. So you cannot, it's undetermined. So whenever you have that situation, your software tells you you cannot fit a linear regression. But ridge regression can solve that problem. Your data is wider than its length. Right? It's not that common in the past, 100 years ago at least. But at least 20 years ago, this thing becomes popular exactly because of all this genetic research. So all this medical research, they see there's 100 patients. They all have some type of cancers. Let's check their genes and see which gene leads to those cancers. You have 100 data points, 100 patients. And you measure the genes of all these guys. Genes are like billions of variables, right? So how do you find that the genes lead to the? You cannot have a billion cancer patients anyway, right? So this linear regression will never answer that question, right? But ridge regression and other regularization methods can solve that. It's pretty much still the only solution, I think. But anyway, that's what makes those things popular. Right? Yeah, the final message is we are trading off between the bias and the variance. We are sacrificing bias, and by sacrificing bias, we are gaining in terms of the variance reduction. Right? And if we find the optimal lambda, hopefully we can improve the overall performance. And even if we cannot, we can go back to the original solution. We don't lose anything. Right? So next question is, how do we find the optimal lambda? Right? Yes? No, that's all out. In sample, yeah, in sample. Bias has no in sample and out of sample. Bias just said, if you assume a linear model, you're using a line to fit the data, but the data actually is curved. What's the difference? What's the best line? What's the error when you do with the best line? No, the trade-off is there. The trade-off is there. And so we're still living in the linear world. So we're changing the lines somewhere. So there's no magic, right? So the trade-off is there. So let's see, how do we find lambda? Right? So this is the picture we have just seen in the example. We are sliding left and right, trying different lambdas. Then we will have the mean squared error somewhere. This is lambda goes to 0. This is the high bias, low variance. This is high variance, low bias. Right? So our hope is by sliding in around, we should be able to find an optimal point that is better than the two extremes. Right? So that's going to give us the optimal lambda. Right? The mean squared error is out of sample. Right? What? Huh? Right? Lambda. This is this is a high variance, low bias. Right? This is the regression. Right? Oh, thank you. This is a lambda goes to infinity. Right? So there's an optimal point. That's what we hope. You can do plot the same thing on a different scale. Right? Let's not spend time on that. And so in practice, earlier, because we are doing simulation, so we can simulate a big test data set, directly measure the out-of-sample mean squared error. In reality, you cannot do that, so you do cross-validation. Right? Later we'll do that cross-validation thing. And we'll talk about most of the things. The conceptual benefit, the trade-off, bias variance trade-off, and the shrinkage idea. So those are conceptual things. So the next thing, the next benefit is in terms of computation. Right? So we are using this to replace the subset selection method. Let's think about what are the difference in terms of the computations. And subset here, earlier we mentioned, the crazy ones are within groups, right? When you have p number of predictors, there's a p times p minus 1 models you need to compare, right? When p goes large, this thing goes crazy, right? This is a combinatorial, because every predictor you need to make a 0-1 decision. So this problem doesn't scale with your data. You can solve that with 20 predictors, but not 200 predictors, right? It doesn't scale. See what we have here. if we have a problem with 20-dimensional. If we have a lambda, how many times do we need to solve the optimization? If we have a lambda, we just solve that once. We get the 200 betas, right? And that's once, regardless of the dimensionality, right? But we still need to find the lambda. But when we find the lambda, we say we try 100 values for lambda. We find the lambda. So this is 100 runs. 100 runs, regardless of the number of predictors you have in your problem. Right? You can have 20 million predictors. You still solve that 100 times. Right? So at least the number of computations is contained, right? Is fixed. And that's an important thing. And at the same time, it solves the problem when you have a lot of predictors. Right? So that's the computational benefit. So with that, we no longer need the binary decisions and all the combinatorial. Right? All right, so that's ridge regression. Any further comments, questions? All right, so let's move on to even better one. So ridge regression is nice in pretty much all sense, but there's only one issue. The one issue is if you go back and look at the solutions, look at these guys. There are a bunch of variables staying there. They have a tiny coefficient. In traditional linear regression, probably they are the insignificant guys. We have already taken them out. But in the ridge regression, they stay almost forever. And towards the very end, they disappear with other important variables. So in some sense, people don't like this because it doesn't really choose the variables. If you have 20 variables, the 20 variables stay in your model pretty much forever until you reach the last, the final day of the Earth. But in the middle, you can see like it's really, there are a lot of variables, they're having a tiny coefficient. They don't really affect your prediction. But just like you are not, in this whole construction, you're not incentivized to say, let's just get rid of this guy. Because you are paying in terms of the beta. This guy has a tiny beta. You get rid of that guy, you don't save a lot. So that guy still has some tiny contribution there. Right? So that's a main critique on ridge regression. So the penalty term, no matter how strong you set the penalty term, it doesn't differentiate the good variables and the bad variables. It doesn't kill the bad variables first and keep the good ones. It just ranks everybody pretty much equally. Everybody goes down. Right? It doesn't differentiate. And therefore, it doesn't do variable selection. We hope it says, up to this point, this variable should get out of this model. Set the beta to 0. But it doesn't do that. Right? So to overcome that, here comes the lasso. Lasso is somewhat, ridge is invented in the 70s. Lasso is about 90s. Right? In statistics, these are relatively young stuff. Lasso says, yeah, to solve that problem is easy. I can do some tiny technical tweak. What I'm doing is I'm changing the penalties. Earlier, I'm penalizing on the square of the betas. Now I'm penalizing on the absolute value of the betas. That's the only change. Right? Everything else remains exactly the same. Right? So let's see. What's the difference? And earlier we just said this is the L2 norm. This is L2 norm. And the absolute value here is actually so-called L1 norm, is beta 1 plus beta 2. It's also a sort of distance in mathematics. Right? All the norms are mathematical distances. And this is L1 and L2. later I'll show you L0 and L infinity. But there are just different ways of defining distance. But why? Well, what's the difference? Why it helps you to do variable selection, right? The idea. This is the consequence. Let me talk about the consequence, and then we talk about the why, right? So the consequence is by replacing that square term with the absolute value, the model tends to choose the variables to squeeze to 0 first. So the previous model squeezed everybody equally over time, right? This one, I kill this one first, then I kill the next one, sequentially, right? Not the, so that, and the consequence is you will get a sparse model. Sparse model means at your optimal lambda, several of the x were ruled out from your model. They have a 0 coefficient, right? So that's nicer in terms of the output, easier to interpret, right? And yeah, it's just simpler to interpret, and people like those things instead of a bunch of x with tiny coefficients. Right? Don't know what's going on. So that's the outcome. Because of the absolute value thing, this is the kind of the trajectory when you increase your lambda. Right? It's still the same picture. This is lambda goes to 0. Oops. This is lambda goes to infinity. At the very left end, they should be the same linear regression solution. But at the very right end, it's also the same. This is the null model. But in the middle, the trajectory is not the same. You can see there's tiny predictors in the middle. They got killed early on. And the next one is the black guy. Then the next one are these yellow and red. And the blue one is the last one survived towards the end. Right? So when you have your optimal lambda somewhere, your model is way smaller. You only have 4 predictors. Right? The smaller ones there. Okay? That's the consequence. Right? We haven't explained why, but that's the outcome. The outcome is a smaller model. It chooses the important variables along the way. If I have less money and less money, or the stuff becomes more and more expensive, I want to not buying that. I want to go switch my budget to the important ones. Right? So that's the story. Why it works? We have an explanation, like a visual explanation related to the earlier pictures. Let's think about this is also optimization stuff. Let's first rewrite the ridge regression problem in an equivalent but different way. Right? Earlier we said in ridge regression we have 2 objectives. We want to minimize the 2 at the same time. But that's equivalent to say I minimize 1, but subject to the other one to be at most that much. Right? So the earlier one we say there's a cost for increasing the slopes. That's the amount of money you need to pay for each unit of beta you increase. And that's equivalent to say you only have this amount of budget to allocate among the betas. You have only this number. Your total beta cannot be beyond that number. Right? So there's a one-to-one correspondence. So this is the standard optimization stuff. How do you reframe the problem? So now the problem becomes, I'm still minimizing the residual sum of squares, but I cannot travel very far from the origin. I have a constraint that says I can only go this far away from the origin. So I have to stay in that circle. Right? I have to stay near the origin. I have to stay in that circle. So given that constraint, what's the optimal solution? Right? That's ridge regression. And if you view the problem that way, lasso can be done similarly. But now my budget is not on the square term, but on the absolute value term, right? So this way we can visualize the constraint, right? This is how we visualize the constraint. For ridge regression, we just say you have a budget. You can move around everywhere as long as your distance to the origin is at most s, right? So what is s here? This is the s here. Let me use it. Okay. So you have a budget. Your total distance from the origin is at most s. So you have a circle. You have to stay in that circle, right? If you have to stay in that circle and you want to get as close as you can to the bottom of that ball, the optimal solution is this guy, right? That you want to go as lower as possible to the bottom of the ball, right? That's the best thing you can do. So that's the ridge solution. And the distance is exactly s, right? That's your budget. You want to use up your budget. You don't want to save here. Are we okay? So that distance measure is driven by the constraint. We have a beta. So we're basically saying beta 1 square plus beta 2 square less than or equal to s, something like that, right? That's the distance. Can be at most that much. Then geometrically, that's a circle. And for Lasso, what's the story? Lasso says absolute value of beta 1 plus absolute value of beta 2 is less than or equal to s. It may not be the same s, right? Let me use a different number. What do we mean there? So we say this is the L2 norm. In mathematics, L2 norm of a point is the distance, straight line distance to the origin. That's the L2 norm. Right? This is L1 norm. You have a point. What's what in terms of a this is the absolute value of beta 1 plus beta 2, right? So you still need to go to the origin, but you can only move vertically or horizontally. This is the so-called Manhattan distance. This is the Euclidean distance. Right? The Manhattan distance means you're in Manhattan. There's a street like a grid. You can only move vertically or horizontally. But no matter how you turn, you need to go back to the origin. So you can go this way. Let me use it. So you can go this way and this way, right? So that's beta 2, that's a beta 1, right? Your total distance traveled is the absolute value of the sum of the two, right? There are many different ways to travel in Manhattan. You can do it like this, right? But the amount of distance you traveled will be the same anyway. If you just move, you don't take circles, right? So that's the Manhattan distance, right? Given the constraints, given you are in Manhattan and you can travel 10 blocks, right? That's a constraint. You can go at most 10 blocks away from the origin, and the result will be like a diamond. That's the result. Given this diamond, this is A. Given this diamond, the optimal solution is on the axis. Right? You see there's a sparse solution here. The optimal solution under Lasso is this guy. It says beta 1 is 0. Beta 2 is the number, right? So if I have to choose, I will choose to take out beta 1. I only keep beta 2, x2 in my model. Right? So the sparsity is exactly driven by the shape of these constraints. When you have circles, it's more likely your circle will touch the boundary of the ball somewhere in the middle. But when you have a diamond, it's more likely your diamond will touch the ball on the corners, right? Because if you have the corners, it's more likely you have the sparse solution. That's the whole idea. Okay? Going to the other side?
Yeah, I mean on the slope of the diamond.
No. Which point? This point?
Along
Uh huh.
it's only at let's say that sharp edge only.
Yes. Only that point.
So any point in between is not possible.
You want to get as close as to the bottom as possible, right? So this is the contour. This is the lowest contour you would touch, right? Any other point you would touch a higher layer, higher level contour. Right? So you want to go as deep as possible to minimize your RSS. Right? But you have to stay inside this diamond. Right? Which one is there? Still think about this as a ball, but now you have a constraint. Your ball cannot scrolling everywhere. Your ball can only scroll here. And there's a slope. Think about where the slope is going that way. So you put the ball there, it will just slide down and stuck here. Right? Stuck here. Okay? All right. And that's the visual explanation why lasso tends to give you more sparse solution. But ridge tends to keep all the variables out there. Right? So this is the lasso and the ridge. And if we view things in this perspective, what we have done last time when we do subset selection can be fit into this framework exactly and nicely. Let's think about what we have done last time. Last time we have the subset selection. Right? We have again beta 1, beta 2 there. Right? Let's suppose we say we want to make sure the number of predictors is no more than 1. 2 is too trivial. There are only 2. Right? 2 is too trivial. I say I have 2x in my data, but I want to choose the best model with at most 1 predictor. Right? Where do we see this? How do we visualize that? You have beta 1 and beta 2 to decide, but you can only keep one of them. What are the possible regions on this picture? Yeah, good. This is the cross, right? So you can choose a point on this line that force beta 2 to be 0, beta 1 to be non-zero. Or you can do this line that force beta 1 to be 0, beta 2 to be non-zero. Or both are 0. But anyway, at most 1 of the beta is non-zero. Right? So you are forcing yourself to choose between beta 1 and beta 2. So that's the subset selection. Right? That's a subset selection. And in mathematics, this is exactly the L0 norm. L0 norm is like the number of non-zero elements. So beta is a vector. How many beta are non-zero is a L0 norm. And if you say this guy is less than or equal to 1, that means I have a vector, but I can at most choose 1 of the beta to be non-zero. Right? That's exactly the thing. And that's going to be super sparse because you are forcing yourself to keep one variable in there. Right? So there are 3 things, and what we have said is subset selection is a bit too strict. You choose 1 out of 2. You cannot strike a balance between the 2. And all these things, it gives you an opportunity to choose somewhere in the middle. Well, keep the sparsity. Right? So that's so all the three model selection things are put into the same framework. And the only difference is really how do you measure the distance? How do you measure, what are you penalizing on? Right? Here you're penalizing the straight line distance towards, away from the origin. Here you're penalizing the Manhattan distance away from the origin. Here you're penalizing this whatever distance on that. Okay? Yeah. Mm-hmm. Mm-hmm. No, this is what we have done is a superset of the best subset selection. Whatever model you are considering inside the subset is a candidate here, and we are trying to find a better model. Right? So what you would end up here is a special case. So we are optimizing with a larger number of candidates. So you will never go. That solution will never be the best when we have more choices, right? So you never need that anymore. And what time is it? Take a break? Let's take a break. Let's take a break. Let me leave the picture here. Of this circle or the size of this diamond. So the size is determined by this constraint, right? How far you can go from the origin. So they're equivalent to the lambda. If your lambda is fixed, there's a corresponding distance, right? So choosing this distance is the same as choosing lambda. So later we'll do the lambda selection. But given the lambda, they're just equivalent. This is all optimization stuff. So how do we choose lambda? Again, for each given lambda, we can find the corresponding set of betas. So we have our model. We can use our model to predict out of sample. If we can predict out of sample, we can measure their performance. So this is the picture. We have 100 candidates for our lambda. For each lambda, there's an underlying model, a linear formula. And we can measure their cross-validation error, right? So we can say, this is the linear regression, what's the corresponding cross-validation error? This is the null model, what's the corresponding validation error? And in the middle, they're all the same. Yeah? For each vertical slice is a model. Just a model, we can measure their cross-validation error, right? Just do the stuff we talked about earlier. So at the end, we say we can choose an optimal lambda based on their cross-validation error. The lambda gives you the smallest cross-validation error is the best lambda. Because cross-validation error approximates the out-of-sample error. Right? So alternatively, if you don't think about this way, just think about this is 100 different lines. After 100 different lines, I don't know which one is the best. I just throw all these 100 lines into cross-validation and choose the best line. Okay? There's nothing more complicated than that. And once you have that, you can go back to your original plot. Since you know what is your optimal lambda, you have your optimal model up there. And there are a bunch of things in there. Right? I think this is the rich regression. And for lasso, that's similar. Somehow I took a different plot on a different scale, but that's the same story. Instead of plotting against lambda, I'm plotting against this relative measure. But you find an optimal spot minimize the cross-validation error. And that's going to be your model. And you can see there's a clear difference for lasso. You only keep 2 variables in your final optimal model. Right? The others are selected out. Right? They're ruled out. Is this clear? Okay. Okay, so we are done with ridge regression and lasso. They have a tiny difference in terms of the model construction is how you measure distance, and the output, the difference is how sparse your model will be, right? Do you have a subset of the predictors or everything in the model? The third model is a so-called elastic net. There's nothing new. We just try to combine the two together. Earlier we said we have a penalty for L2 norm, L2 distance. We have a penalty for L1 distance. Now we have both. That's it. There's nothing special. Some belief is that by combining the two, we are taking the advantage of both. Right? Or at least we have more flexibility to play with. Before you have 1 lambda to determine, now you have 2 lambdas to determine. That's not a trivial thing, right? 1 lambda you choose 100 values. The other lambda you need to choose another 100 values. You have a 10,000 values, 10,000 models to compare, right? That's not a trivial thing. And in practice, people don't, even when people do elastic net, they don't like this way of presentation. So writing this way is easier for us to read, because this is clearly a combination of the 2 models we have just introduced. But in practice, people do this way. So instead of framing the problem with lambda 1 and lambda 2, we frame the problem with lambda and alpha. So lambda is the similar thing as we have. But in the middle, the penalty, the distance thing, is a combination of the first one and the second one. And the combination is controlled by alpha. Right? So if you see when alpha is 0, you don't have the first term. You only have the second term. You go to the ridge regression. When alpha is 1, you don't have the last term, but you have the first one. You go to lasso. And when you choose somewhere in between, you get a combination of the 2. And how to choose, again, you need to do cross-validation to choose your optimal alpha. What's the combination of ridge and lasso? This 2 is a constant. That doesn't matter, right? It just for the sake of that the algorithm is easier. When you take a derivative, you get a 2 canceled out, right? There's nothing special. So at the end, they're not combining the 2 penalty terms. They're combining the 2 derivatives. The derivative is alpha and 1 minus alpha. All right. So that's the 3 models we have seen. The third one is a simple combination of the first 2. And they all solve, at least lasso solved that problem of the so-called simultaneous variable selection and parameter estimation. It's beyond the regularization. It's a parameter. Think about there are 2 tasks. We choose the variables to be included in our model. Then we estimate the coefficients, betas. Right? In the past, we treat these 2 steps as separate steps. We have a big table to choose which model to include, given which variables to include. Given the variable choices, we need to run regression to figure out their corresponding betas. So there are 2 steps, variable selection and parameter estimation. And that makes that computationally crazy, a lot of things to do. But here in region lasso, it does that at the same time. So variable selection is not that special in the sense that we're not doing 0, 1. We're just controlling the beta. Up to some point, the beta goes to 0. That basically means you decide to delete that. Right? So earlier, the decision is like, do we keep that or not, 0, 1? Given that we choose to keep that, what should be the coefficient? Right? That's 2 steps. That's less intuitive. Here, it just choose the beta. And if you want to delete that, just set that beta to 0. Right? So that's just everything in one step. And regularization is, in general, a big idea. What we have seen today is the regularized linear models for linear regression. The homework for you today is the regularized generalized linear models. So you need to do logistic regression. That's exactly the same thing. Logistic regression, at the end of the day, you're finding the betas. Right? Now you say, I want to do regularization. I want to penalize on the big betas. The same thing, right? Same set of a code, actually. So at least it works for linear regression and generalized linear models here, yeah? Because you have the same linear structure. Next week, we will talk about the trees. When we talk about trees, and this also neural network, we're not going to talk about. But those are models with parameters in there. And the regularization can be applied to all these models with parameters. Just say, I don't want my parameters to be too big. I want to shrink my parameters. Next week, we'll talk about trees. We'll have that. Yeah. But this is just a general idea. Whenever you have parameters, you can say, I want to regularize that by pressing the parameters to be 0. So that's, I'm controlling the size of my model. Mm-hmm. And the things make this tools famous is it can solve the problem with wide data. Okay, let me talk about this, and we go to the coding part. Right? Group project. So we have done the test, so now it's the time to think about a group project. Also, after today, you have already a complete set of tools to do your project. Later, we'll have more fancy tools, but you can plug in that later. The whole framework is done from the very beginning to the very end. Doing a model selection, cross-validation to do model selection. Everything is there. Later, you can add more tools. So in that sense, this is a good time to think about your project. So let me just describe the expectations. There are 20 points on this project. So I'm roughly allocating the 20 points to these 4 different components: problem definition, how important is your problem, how creative it is, the execution, and this is like choose the right tool, do the right things technically, and the report is about the summary of the findings, the high-level messages, and then the 5 points on the presentation. Okay? Fair enough? It's just a rough thing, right? So in that sense, the first 15 points are based on the written report, and the last 5 points are based on the presentation. Right? So the report, I expect a concise report. So I'm imposing a penalty term on that. So that's regularization, right? Just like in the exam, I have a regularization for the exam time. So that's also there's a penalty for extra pages.
How many pages will have no penalty? You cannot say 2 pages, they got penalty already, right? So
No, the right question is, what is your lambda? It's not about the constraint. It's about the cost. How many dollars for each extra page? I don't know. Imagine. You need a cross-validation. Yeah, but in general, don't waste your time write a long report. I'm very impatient in reading. But treat your report as a technical appendix. Leave all the high-level messages in your presentation. I think you have 15 minutes to present, so that's enough to talk about how important and what are the findings. Treat your report as a technical appendix. The technical side, you don't have time to talk about in your presentation. That's enough. The code and the exact data part. Right? There's no need to write a long findings and conclusions and executive summaries or all those things. Right? So in that sense, that's a markdown with some code and data is good enough. Right? So as long as I can go in and check what you are doing, right? There's enough information I can check what's wrong, what's correct. That's good enough. Right? And leave all the other soft, high-level messages in your presentation. So prepare a 15-minute video, upload that to VLE towards the end. High-level messages, not technical. The only expectation, I hope all the team members to show their face. So the deadline is November 26th. I just leave myself one extra week to do the grading and summarize everything. That's the last possible time I have to submit the grades, right? And the deadline for report and the video, right? Both. Okay. So you can think about what are the. For now, think about what are the problems you want to study. It's better to communicate before you really start, because in the afternoon class there were several students asking about there's such a competition on Kaggle. Can we take that? I said, yeah, in general I don't mind, but I went and checked the competition. This is a kind of a bad competition I don't recommend people to take. You get 200 columns of X, but there's no physical meaning. X1 up to X200. So the task is to generate a prediction. What's the point of doing that? You have no idea what you're doing. So try to find some problem with some context. Right? The important thing is to understand the context and to get your understanding about the problem into your solution. That's important. I find this is really strange, those people. Last time I also had that, one team was doing that. And they were finding people discuss. So Kaggle is the website hosting all the competitions, right? And they have an open forum, people discuss. So everybody work on that project, discuss in that forum. This one guy posted, I found a good feature for prediction. This is X3 plus X4 divided by X26 is a good feature. So there's a lot of trial and error, and you don't know what you're doing. So don't waste time on those things. Find something with a context. It doesn't have to be business problems. I don't mind having some crazy applications, but there should be some background. If it's sensitive, you can, yeah. What kind of things you have in mind?
Do we need to submit the data set into?
Yeah. If it's not sensitive, if you have a drug dealer saying, don't send it to me, I don't want to die. All right. Yeah, just let me know whenever you have something in mind. We can have a quick chat about is this the right direction to go, right? Before it's too late. Right? Okay. No more questions, no? Okay. Now coding. So what we're doing today for illustration is the baseball data set we have done with subset selection. Right? Last time when we do best subset, we used baseball data. So the whole idea is we're going through the ridge regression, lasso, and elastic net at the end, we'll have our best model. We'll compare this best model with the best model we have found by subset selection. Yeah, you will see there's a fundamental difference, and yeah, we'll see. And this is a regression problem. Last time we said this is about the baseball players and their salary. We have done this last time. There's some missing data about some players' salaries are missing, so we're deleting those guys. So at the end, we have 263 players, 20 columns. One column is the salary, is the Y. When salary is the Ys we are predicting. All the other 19s are predictors. So we have P is 19. The majority of the predictors are numerical. There are several categorical ones, which league, new league, and division. Right? So if you want more context, you can check the help of this data set. It explains each of the variables. But yeah, it's mostly about the statistics in their whole season. How many hits, how many home runs, all those things. Okay. So we will do step by step several things. The first thing is I'm doing a lot of extra things just to illustrate what is available in this whole process. Later you will see if you want to do a lasso on this data set, you need 3 lines of code, just 3 lines, right? I'm having a lot of extra lines just to show you there's several other things. So when you do your homework, you don't need to copy the whole chunk of code, right? You should be able to identify which ones are important ones, which ones are not. And the other thing is lasso. These things are in this package called a GLMnet. If you don't have that, you can try to install that. So GLM stands for Generalized Linear Models. So it can work on regression, logistic regression, postal regression, everything exactly the same as the GLM we have done. Net means the elastic net. So here there's actually only one function coding the elastic net. So you can choose your alpha to be 1, you get the lasso. Alpha to be 0, you get the ridge, or some other alphas, right? So there's only one set of functions. The bad thing about this function is that it doesn't take the formula thing we are used to in linear regression and generalized linear models. So we have to do that manually. But it just adds one extra line of code. So I'm showing you the first thing is, so the function GLMnet expects x and y separately, just like a k-nearest neighbor, in a matrix format. So you have to do the conversion before you start to running this. So, but this thing can be done by the function called the model matrix. So it just does that thing for you. You can check the help, but let me just do that. You can see that's pretty straightforward. This is the way we were used to when we were doing regression. Right? Tell me what's the data, and what's your model. The model, what's the y's, what are the x, right? So this is what we used to do. And since GLMnet doesn't take this data, so we can just have an extra line of code. Model matrix can convert what we used to do into the required data, right? So this is an illustration. If I'm doing salary versus hits and league, hits is the numerical variable, league is a categorical variable, 2 categories. So if I'm doing that, I've saved the output into this M. If you check, M is a matrix with 3 columns, hits and league. League was the categorical variable. Now it's converted into a dummy variable automatically, 0, 1 dummy variables. So that's exactly what linear regression has been doing internally. But here you just need an extra line to do that on your own. But the issue is there's also a column of constant ones. This is for calibrating the intercept. And the lasso stuff doesn't want that column. It only wants the real x in your model. So you have to delete the first column. So what I'm doing here is by adding this part. So you just say, I'm selecting this whole matrix with all the rows, but all the columns but the first one. Right? -1 means other than the first column. Right? So I'm just taking out the first column. And now that's what I need. If I have 2x, I have 2 columns. Okay? And internally, you can see this is a matrix with 263 rows and 2 columns. That's what you have. Okay? So that's a quick illustration of model matrix. Now let's do that for our model. So we are predicting salary using all the other predictors. So I just use the dot. Dot means everything else. Right? I'm taking out the first columns. So that's going to be my x. That's my x. This is a big matrix. I think it should be 19 columns, right? My x has 19 columns. That's here. Right? And y is easy. Y is just a salary column. So I just take that column. Y is just a column of numbers. Now we have x and y. If you check here, y is 1 column, x is 1 matrix with 19 columns. Right? So we can now start doing GLM net. You can check the help a little bit and give you some task for the homework. When you do, when we do linear regression here, we don't need to do a lot of things. But today's homework is about a logistic regression. So you need to choose your right family binomial, just like the logistic regression we have been doing. You can do Poisson, multinomial, all the others. So you can check the documentation, try to learn a new package. Right? Let me do the regression part. And the only information you need to supply is what is your x, what is your y. This is we have already prepared, and what the alpha. Alpha for, since here we are doing ridge, so alpha is 0. Right? Later we'll just change that to 1, we get the lasso. Okay. So I'm saving that to an object called the ridge model. Inside there are a lot of things. Let's not spend time on that. We don't need, unless you want to dig out some information. But the standard step is to do a plot. Plot, you get what we have seen in the slides. And remember I said this is not standardized coefficient, it's coefficient. Right? This is fixed. It's just a coefficient. So it's just a betas for 100 lambda values. And this is log lambda. It's on the log scale. Yeah? Why I say there are 100 lambdas? Earlier, we said there's a ridge model object. Everything is 100. There's 100 lambdas. Where are the values? Here. These are the lambdas it tried, from some huge number to all the way to almost 0. There are 100 of them. Right? And that's done for you automatically. You don't need to worry about how do I choose my lambdas. It just automatically find the minimum, maximum, cut them into 100 chunks. So that's pretty much all transparent for you. Up to this point is only illustration. Right? When we do our real analysis, we don't do all these things. Right? Just to show you what's available. So you can imagine in this ridge model, there are 100 models in there, 100 linear models for these 100 lambda values. For each model, there are 19 betas plus the intercept. There are 20 betas in total. Right? So you can see the dimension of the coefficients. You have 20 rows and 100 columns. Right? That's 100 models, each model with 20 numbers. You can see all these values, but not so important. Again, here is just to illustrate if you want to pull out, you know this is 100 models. If you want to pull out the 50th model, you just say, give me the 50th model's lambda. Lambda is a vector with 100 values. Right? Just give me the number 50. This is the corresponding lambda. And what about the corresponding betas? So this is the coefficient of the 50s model. So that's the beta. Right? These are 20 betas. Right? And if you want, you can calculate the penalty term, sum of all the betas squared. I don't know why you want to do that, but just to show you, you can. You can do the same thing for the 60s model. Makes no sense to do that. So these are the models with 100 automatically chosen lambdas. You may say, I want to give you a lambda, tell me what's the corresponding model. Right? So that's here. That's a predict. You can use that model. You say, now I want my lambda to be 1,000. Tell me what's the coefficient. This is a predict, but predict has multiple meanings here. Predict can be used just like before with linear regression and the generalized linear models. You can predict a response. You can predict a link in generalized linear models. Here we are predicting the coefficients. It's actually printing out the betas. So you just print out the betas. They say, if I want my lambda to be 1,000, give me my model. That's a vertical slice with an arbitrary given lambda. Okay? Okay, now we get to the real part. The real first step is after you do the model matrix. Model matrix is the first line. Convert your data into X and Y. The second line should be this cross-validation. Once you get your data ready, you should do a cross-validation to choose the optimal lambda. Right? The second line should be this. We need to do cross-validation. So there's a function called cv.glmnet, just like cv.glm. That's the cross-validation for you, one line. Okay? So we can just do that. What are there's nothing to read here. So cross-validation by default is tenfold, right? What is k? What is n-fold? N-fold default is 10, right? You need to read this a little bit. By default is tenfold, so we are doing tenfold. We don't need to do anything. It's random, so I'm setting the seed here. So this is one line, the second line of code you need to do. Tell me what's your X and Y and what's the alpha. What's the model you're doing. It's automatically doing a cross-validation and give you a plot like this. So this is automatic, right? So that's the second line of code. Plot is not necessary. Right? I'm just showing you. This is the cross-validation error for these 100 lambdas. Right? The 100 models was the cross-validation error. And there are two vertical lines indicating, the first one is the minimum. The lambda that gives you the minimum cross-validation error. Okay? I forgot to say, the red line is the average cross-validation error. So internally, it's repeat things several times, I think. So for each point, you have multiple numbers. Red line is the average. And there's also a standard deviation. It can be seen from here. So I have run this cv.glmnet. I save the results into rich.cv. Okay? So if you open that object, you will see the lambdas. This is a 99 lambdas, slightly different than before. I don't know why, but it seems like the same values. Then this second item is a cross-validation error on average. So that's the red line. For the 99 models, you have a 99 cross-validation error, the mean. Also, you have the standard deviation. The standard deviation of the cross-validation error. So that's if you look at the picture, that's the spread here. Right? And then you have the CV up and the CV low. That's the mean plus standard deviation and mean minus standard deviation. That's how you plot these two lines up and down, the two lines up and low. Right? And where are we? So we just said the first vertical line is the lambda giving you the minimum cross-validation error. There's another vertical line. This is the tricky one. So first of all, lambda going left is less regularization, linear regression solution. Lambda going right is more regularization. Right? The larger the lambda, more regularization. The more sparse model, less smaller coefficients. Right? So in general, people don't like this lambda. This is the lambda minimize your cross-validation error. But people say there are a lot of variability here. We shouldn't just trust this point because there's so much fluctuation. And since we want to have sparse model and smaller model, we should push a little bit further to the right. But where to push? So this is a heuristic. There's nothing theoretical. People say, I have the minimum. I raise the minimum by its standard deviation. I get the CV up. Right? And this is the level I can trust because I'm sure they are below that thing. And I'm moving that level to the right and find the intersection point. So that's the lambda gives you an average cross-validation error that is one standard deviation above the minimum. People say since there are all these fluctuations, you have no idea which one is better, which one is worse. So let's go further to the right and choose the second one. Right. So that's a rule of thumb kind of thing. The motivation is I want more regularization because I don't want to make my decision purely based on this minimum. I would rather take a more conservative step and go to the right. Right? There's no right or wrong, so they will give you the two lambdas. It's actually hidden here. There's a lambda mean, that's the first one, and there's a lambda 1 standard error, that's the second one. So that's one standard error higher. So you can choose, depending on your context, whether you want a more sparse model or a more accurate model in some sense. Right? But the whole point of this second line of code is to choose your lambda. Right? Now you have all these things, you need to make a decision. I think in the following, I will choose the second guy. But that's the second line of code. We have a lambda. Just for example, if I'm choosing the first one, lambda mean, I can put it out. What I'm doing here. I'm just plotting a point, just highlight this is the point I'm selecting. Right? Nothing special. I can also highlight the other one. That's the other point. What do we do with that? I can also highlight the two lambdas on my original plot. These are the two vertical cuts I want to do, depending on the models. So you can see the sparsity or the regularization is very different between the two lambdas. Right? The magnitude of all these coefficients are very different. So you need to choose one. But whenever you choose the third line of code is this one. Once you choose your lambda, you just need to predict the coefficient. I have chosen my optimal lambda. Tell me what's my model now. So that's a vertical thing. Right? Here I'm using the lambda 2. So you just say, using this particular lambda, tell me my model. So that's the model. Right? That's the third line of code. We are done. Construct the data, cross-validation, and set your optimal lambda, right? Whatever you like. So that's the final model. That's the right side one I have chosen. And this is a ridge regression. You can see we just said it doesn't do model selection. All the 19 variables are there, but a lot of tiny coefficients. Right? That's what people hate. It's kind of a strange. You keep all these tiny coefficients throughout. Right? And that's the predict. Here I just say alternatively, you can predict with this ridge model. just keep in mind, we have built two models earlier. One is using CV-GLMNet. So this is the second line of code I have mentioned. This is a rich CV. Earlier, we built another model, use GLMNet without cross-validation. Okay? You don't need to do this part. I just say, yeah, if you have that. So you can just do CV-GLMNet, choose your lambda, then predict your lambda with that model. That's it. Right? 3 lines. All right, any questions? Yeah, just that 3 lines, right? So next we will repeat the 3 lines with lasso. The only thing we need to change is to change that alpha to 1. Right? Again, this is not necessary. This is only necessary if you want to visualize this plot. You want to build a model to plot, to see this thing. Right? So what is really the key is the CV-GLMNet with alpha being 1. So we have these two. The effect of choosing lambda 1 standard error is not so obvious earlier because it just squeezes the betas. Right? It doesn't really choose anything. In lasso, it's going to be very obvious. I'm again plotting all these points. Just skip that part. So let's see the 2 models, right? And these 2 models are super different. Right? I'm again choosing the right-hand one just for the parsimony. I want less variables. But you can see the coefficients and the set of variables are very different. So third line of code, this is my final model. I only have 5 variables. Right? So in lasso, if it's 0, it doesn't display. You only have 5 non-zero betas. And actually, maybe only 2 are very important. The other ones are tiny, kind of. No, by the way, the magnitude doesn't say anything. Right? This is a unnormalized coefficient. Right? So we shouldn't interpret their importance by the magnitude. Okay. All right. Then that's lasso. Later we'll compare the set of the solutions. Right? Let's do the elastic net. Elastic net is basically choosing an alpha that is non-zero, non-1. Right? I put a 0.5 here. Repeat the whole thing. You can imagine this is the combination of the first 2. If you do that, you will get slightly more variables. 9. I have 9 here. Right? Those are trivial things. So the real question for elastic net is, I want to optimize my alpha. I don't know how to choose my alpha. Or to put it differently, I don't know whether I should use ridge or lasso, or somewhere in between. Right? I want to choose my alpha by cross-validation. Unfortunately, it doesn't have an automatic version, so we have to do that manually. Right? If you want to do that part. So we will do a manual 10-fold cross-validation. Don't worry. This is extremely simple. All you need to do is to cut your data. You don't have to do this, right? Earlier we said you can measure the performance for any given alpha. We put a 0.5 there, we get all the things we want. So you can enumerate all the possible alpha and choose the best one. So that's a quick solution. But the concern is I don't want to do that. It's exactly when we do cross-validation, we were thinking about the sequence. We want to cut the data first, then compare the models on the same data partition. But if you just do the earlier way, you say alpha is 0.1, partition the data, estimate. Alpha is 0.2, partition the data, estimate. That's not very fair. Right? So all that I want to do is I want to partition the data in my way. So this is last time we do 10-fold cross-validation with best subset. We have done this part. We have 263 data points. We allocate them into 10 groups. Right? We save the allocation into this variable fold. Right? That's the fold. And the beauty of CVGLMNet is it doesn't have to generate a random partition on its own. You can tell him, this is my partition. Go and use this partition to do cross-validation. Right? So that's the beauty. So I basically generate the partition at the very beginning. Then I'm looping over all the alphas. For each alpha, I'm calling CVGLMNet. This is my X, this is my Y, this is my alpha. But the extra thing is this fold ID. So you can tell CVGLMNet, this is my way of partition the data. Use this way throughout. Right? So I'm comparing this different alpha model with the same partition. Right? That's later we'll have several functions having these nice features. So you don't have to do manual things. And I'm comparing 11 different alphas. You can make it longer, but it's just illustration. For each alpha, I'm building the models, and I'm saving 2 sets of data, the minimum lambda and the one standard error lambda, and the corresponding cross-validation error, just a red line, right, for the two things. And at the end, this is what I have. Alpha goes from 0.1.2 all the way to 1, right? And if you are choosing the minimum lambda, these are the lambdas, and these are the cross-validation error. If you're choosing the one standard deviation, these are the lambdas, these are the errors, right? I'm choosing the one standard error guy. I'm choosing that optimal lambda and the optimal alpha. And I can plot it out. Right? So that's the 11 models I have compared with different alpha. And this is the cross-validation error at this lambda 1 standard error. And it turns out that 0.9 is my best model, right? Alpha being 0.9. With that, I can build my final model again with the optimal alpha. And that's the model, right? So I can do a prediction, show the coefficients. That has 6 predictors, right? Lasso is when alpha is 1, has 5 predictors. We are going a little bit backward. Alpha is 0.9, right? We have 6 predictors, right? So these are the best model within these families. We have optimized everything. Optimized alpha, optimized lambda. This is the best you can do. You get a linear formula with 6 predictors. Okay? So the last thing is to compare that with our conclusion last time. Last time we did the best subsets. And the best subset said the optimal number of predictors was like 10 or 9. 9 here, right? There are 9 variables. Not wide enough. There are 9 variables chosen by the best subset, and their corresponding coefficients are there. Now let's make a quick comparison. First one is 80 bet 0 in my model, minus something earlier. Hits 6 in that model, hits 1.5 in my model. Right? Walks 5, walks 1.7. Right? And this is the regularization. We squeeze the coefficient to a very low level. But turns out this is more accurate auto sample. Right? And I guess there's no coefficients with different signs. 80 bet, not there. C runs, almost nothing. CRBI, C walks, no. Division. Yeah, there's no opposite signs, right? But the magnitude are much smaller, right? Does that change your view of the world? Huh? people in the old school have been using this as the best model. They've been making up all the stories about what are the impacts of all these variables. Every extra hit, you make $6 extra, something like that in your salary. But what's the value here? Right? That's the difference. Right?
Normalized coefficient.
Yeah, the same thing. Yeah. Just on the same scale. For this data is too small, so we don't have a test data. If we have a test data, we can compare these models in terms of their out-of-sample error. That's your homework. So you will have a test data, so you can compare the model coming up from the traditional method versus the model coming up from the regularization method. And you have a smaller model, less variables, smaller betas, but it works better out of sample. Right? So it just basically says all the things up there are driven by noises. You're getting a lot of noise and you're fitting steep lines. Right? But at the same time, people from the old school really hate this thing because you just give me 6 numbers. How do I tell all these stories? P-values, confidence intervals, nothing. That's all I have. I can write this formula, that's it. How do I say anything about it? Yeah. So there's some people criticizing this model. In 2 weeks, we're talking about the bootstrap. We're talking about potentially how to obtain a confidence interval kind of thing. This is an easy way to do that if you want. Right? But here, that's it. There's no more significance. P-value. That's the model. Predicts the best. Right?
Why isn't there any p-values?
It doesn't exist in this whole model. This model is about finding beta, makes the best prediction. Why do we need a p-value? If it's not important, it will be killed. Those are killed, you can say they are not significant. In that language. Huh? Yeah. There's no p-value. Forget about those things. It's not healthy. Uh-huh. There's no such definition of p-value. P-value is about what's the chance this coefficient is driven by noise, right? I don't have that. Give my data, this is my best model. That predicts the best, right?
You know, the traditional models, for example, that after you have done this, there's something like R-squared, adjusted R-squared, that, you know, it tells you that, you know, whatever the prediction, the R-squared, no matter how you predict, probably is only 20%.
Yeah, yeah. Mm-hmm.
But over here, this, you know, after all this variable coefficient, how do we know that actually this?
You can do R square. You can do R square easily. So eventually, this is a line, right? It's a line you can predict in sample. You can measure your R square if you want. And you can use your cross validation error. That's the out of sample mean squared error. That's also a measure of how good is this line, right? So you can compare this with a random forest. Next week we'll talk about random forest. How do we compare those things? Their cross validation error is there. I can always compare all these things in terms of their cross validation error. Right? So the performance of the model is there, but inside the model, that's all. Yes, yes, yeah. Internally, it scale all the x, run everything, then scale the beta back. Right? Yeah. So you don't need to worry about that. Automatic. That's a necessary step, so they have to code that. I just wonder why not code this model matrix into that. I don't understand. Anything else? Yeah. No, it's automatic. It's done. for you automatically. Don't worry about the data. Okay.
What does the geometry of elastic net look like? Because we have
I forgot to plot that. It's there. Let me do that here. So the question is, what about the shape of that? Right? Earlier we have a diamond, then we have a circle. What about a mixture? A mixture is just a mixture. No, I'm not done yet. Mixture is somewhat like this. I'm bad at drawing this thing. Does that answer your question? Well, that's a mixture of that, right? Think about this. That's a football. You can inflate that. Alpha is how much you inflate that. But roughly, yeah. All right. Anything else? The other, there's one thing we didn't talk about is we started out by assuming we have a set of X, right? When we do linear regression, we actually talk about other things, like shall we include a square term, cubic term, interaction terms. So those questions are still there. You still need to do that. You still need to think about, in the model matrix part, whether I should include interaction, all those things. But you do that in the first line of code, introducing the. But at the end, the model matrix will convert that everything to many columns of data, right? And the next line of code doesn't know what you're talking about. They're just a bunch of columns. They're just numbers, right? So it doesn't differentiate what's going on. So in that sense, we might lose some, not lose. You might gain some extra flexibilities, like some of the categorical variables. When we do regression, you might have 3 categories, right? It becomes 2 dummy variables. In regression, it knows these 2 dummy variables are coming from the same categorical variable. Like in step AIC, if step AIC decides to take that out, it takes 2 dummies out at the same time, right? It treats the 2 columns as 1 variable, right? But here, when you do this model matrix, it gives you 2 columns of dummies. Then the next line of code just see this is 2 columns of 0 and 1. It doesn't know they're coming from the same categorical variable. So it might turn off one and keep the other. You don't lose anything in that sense. It's just some categories, if they're not significant, you get the beta to go to 0, right? Some are still there. But in some other sense, you might see people from the old school might feel uncomfortable, like the interactions. We said when we keep the interactions, x1 and x2, we also keep x1 and x2 individually. So there, we should use the 3 variables at the same time. But here again, when you do model matrix, they're just 3 columns. They don't know who's who and what's the relationship, right? They might keep the interaction column and delete x1 and x2, right? It's all possible. Because it doesn't have the information about what's the relationship. It just see this is a column of matrix, right? You choose what you choose. Okay? Okay? The homework for today is to use this thing for classification, binary logistic regression. So you need to read the documentation a little bit, because when you do classification, when you predict, it may give you different things, right? The type equal to response or type equal to link. You need to read the documentation a little bit. And at the end, you will plot the ROC or AUC or all these things. But those are standard, right? Compare the lasso model with traditional logistic regression and see the difference.